Good afternoon to all lecturers. I'm Radin, and today I'll be explaining to you about the development of my oscillator heat 1.0. So my project is under Dr. Yip, and my project ID is PI-Oct2024. So this is basically the table of contents. So the problem statement is that currently the traditional heat exchangers that is in the market is increasing the compressor workload due to flow obstruction. So my objective is to develop a heat exchanger that actually improves efficiency while reducing the pressure loss itself. So my solution will be oscillator heat 1.0. So before we move on, I'll explain to you the concept of reverse heat pump. Reverse heat pump is basically using the ambient heat to instead of direct heating of what we have currently, which is the normal electrical heaters. Then for the efficiency factors will be measured through COP, which is the coefficient of performance, and it is heat transferred over work done by the compressor itself. And higher COP will result to more efficiency, and lower compressor load will result into higher efficiency as well. So as a comparison to traditional heaters, electrical heaters is actually using one-to-one direct heating, while RHP heaters uses lower energy due to its indirect heating and using the ambient heat, making it more sustainable for the environment. So like I explained earlier, like what I'm going to mention is key components is basically evaporator, compressor, condenser, and expansion valve. So basically the heat exchanger role in this case is to replace the condenser role to transfer heat more efficiently. So this is basically the schematic of RHP. RHP is basically the water tank. Then it will it's two systems in a sense. This is the RHP system and this is the water tank system. So cold water from the supply will be pumped into the water pump, into the PVC pipe over here. So it will be pumped into the water pipe, and then there is baffles along the way that makes oscillatory flow mixing in the PVC pipe itself. Then it will go here, and then it will go back into the. Then the hot refrigerant from the compressor itself will be pumped into the copper pipe, and then it will heat up the copper pipe through the turbulence happening inside the pipe itself. It will heat up, and then it will be transferred back to the hot water tank. Yeah, so basically the objectives of this project is to design and fabricate a heat exchanger that utilizes oscillatory flow mixing, and it conducts experimental testing between the prototype and also what we have currently in the market, which is the brace plate type heat exchanger. And then we compare the performance between the two. Yeah, so like I explained earlier, it's oscillator heat 1.0. So fabrication process, we use cryopragmatic software to come up with the design, and then I did the machining together with my TSO, Mr. Chong, in that campus itself. So we integrated this oscillatory flow mixing to enhance heat transfer itself. So the dimensions was provided by University of Cambridge, as this was a study conducted by them, that they say that through this method you will enhance the heat transfer process. Yeah, so spacing will be between the baffles will be 75 mm, as I'm using a 50 mm pipe. So this is, for example, the 75 mm. And then the orifice diameter will be 25 mm. So in this case, is this sizing. So the materials that I use is PVC pipe, PVC sheet, and PVC joints, as is the most accessible material that we have in campus and also easily available outside as well. So this is just the designing phase. As explained earlier, this is the baffle, and this is the baffle, and this is the spacing between. So it is 75 meters, then one baffle will be inside. 75 meters, then there will be one baffle inside. So this is to induce the oscillatory flow mixing process, and causes the turbulence in the flow of water inside the piping itself, making it to reduce and disrupt the boundary layer of the heating. Yeah. Yeah, so this is just the machining phase that we do. So basically I cut the steps down to step by step to do all these processes to come up with my prototype itself, together with my TSO, Mr. Chong. Yeah, so this is the initial testing phase. Unfortunately, due to we used a recycled system, hence it wasn't able to provide us with a good enough result that may prove that this prototype is better. Hence, me and Dr. Yip discussed, and we come up with a new final test setup that shows that my prototype is better than the brace plate type heat exchanger. So the materials used for this is the PVC pipe itself, copper tubing, water pump, temperature sensors, and water boiler. Then I will assemble the heat exchanger with the schematic that I will show next, and pump water through the system to test for any leaks. And then after that, we will compare between the two performances of the two heat exchangers that I'm comparing, which is oscillator heat and also the plate type heat exchanger. Yeah, so this is just the schematic of the diagram itself. So hot water will be pumped into the system, and then it will enter. So this acts as for example, in the real system will be a refrigerant. Then it will heat up the pipe, and then goes back into the system. Then for the water tank, we cold water in, and then hot water will go out. Yeah, so this is just a video, a short video of how the system goes. So this is the boiler, this is the cold water tank. Then it will circulate and circulate and circulate over and over again till it reaches the certain temperature. So for me, I start the experiment at about boiling temperature, which is about 100 degrees, but due to the water boiler's limit, it cut off at 100. So I wasn't able to reach the 100 degrees as there's an automatic shut off. Yeah. Yeah. So then I managed to craft up a graph out of it. So as you can see from the orange line, it's performing better than the plate type heat exchanger itself. For the top one, it's actually basically comparing it to the temperature of the supply tank that will go up to almost 100 degrees. Yeah. So basically these are the comparisons between the two. The oscillator heat went from 26.4 to 84.2. Then the plate type went from 30.2 to 76.3. Then when we compare using the QR over QS method, we found that it's 12.154 more efficient than the plate type heat exchanger. But if you use it as a baseline, oscillator heat is actually 25.65 more efficient. Yeah. We also conducted a pressure drop analysis to compare between the two pressure losses that both systems had. So in the initial oscillator heat using Darcy equation, I was able to find that it's only losing 0.7113 kPa pressure loss. But when I did my research on plate type heat exchangers, it's about 20 to about 100 kPa itself. So the impact of pressure loss will result in more workload done on the compressor itself. So the higher the pressure loss, there will be more work done by the compressor, hence increasing the COP itself. Yeah, so this is just a summary of everything that I've discussed earlier. The oscillator heat uses a straight line configuration, therefore of its low pressure drop. Then for the plate type itself, it has multiple plates compressed in one, making it very thin and very tightly, that's why of the high pressure. Yeah, so these are some of the challenges that I faced. So for example, in this case, there were bracing done, hence it melted the PVC pipe itself. And also there were leakages due to the sealing of the PVC pipes. But after using the recycled material of the joints that I cut out, I managed to reinforce these areas with this piping. Yeah, so just a few lessons learned and recommended improvements are maybe material selection. We can go for something that is more durable, and also we should minimize the system losses through leaks and whatnot, even though it accounts for maybe 1 or 2%. Then after that, the recommended improvement, maybe we can use like improve sealing and also conduct further tests on a system that is actually working. So conclusion of my work is basically oscillator heat 1.0 demonstrated a higher efficiency as compared to the brace plate type heat exchanger. It's a viable alternative as the heat exchanger on its own for RHP water heating applications. Then after that, for future works done, I would like to put it into a system and then test it and be able to test the COP directly, so we can see the difference between the two plate type and also my own oscillator heat 1.0. Then we can also see whether we can explore different options of commercial production with better materials, and also implement materials that are more thermal ready. So we can also, for this case, because the line that was the configuration that was given was a straight line, we can actually go for a different design, maybe curving or whatnot, to make it more integrated to the industrial and commercial users. So the potential of these commercial applications is maybe putting it into a commercial context or industrial context for this heat exchanger. Yeah, so this is just basically the same as what I've explained earlier. And then this is just a few videos of how we conducted the experiment and how it flew. But this video is a bit loud, so I didn't reduce the volume, but it's just basically the same thing of water flowing and in and out of the system. Yeah, that's about it. Thank you.
Thank you. Any gentle reminder of
Yeah, correct. I mean, it's really just, I haven't submitted, sorry.
Testing goes to nearly 97 degrees.
98, 19. Yeah.
But those materials you use are not designed for that. The pipes and stuff like
Correct.
that.
There were some leakages during
It's very dangerous, you know,
the,
when if they are going with the temperature and spray out the hot water everywhere.
Yeah, correct. We try to maintain the safety of it. When we were
Usually we go for rigid copper pipes and it's just close to
100.
anything above 80. In fact, actually the PVC is rated for 80. Is it correct?
According to research, I actually say 100 to 260 lah. I mean that's the max.
No, the PVC
Yeah,
pipe rating, the safety rating.
Yeah, safety rating is around that area lah. But because if we test it in an actual system, it will be up to 60 to 70 only. That's why originally I chose the PVC pipe as the original. Just that we had to do the experimental testing to test between the two lah.
You still have to think about the overall the safety issue with hot water, especially the hot water spray everywhere, very dangerous.
Could other materials be used?
Definitely. We were planning to change to other different types of material, maybe Teflon, maybe something like sheet metal, or maybe even copper in the future. Maybe in the upcoming projects that's taken over me. Yeah.
Can you go back to a few slides where you are talking about 1.0, the efficiency is about compare one.
Yeah.
Okay. So you mentioned that the 1.0 version is more efficient by 12%, whereas they are using 30 plate, right? It's 25.65 more efficient. So you are comparing your 1.0 against with the plate type.
Yeah, correct.
So from what you are saying here is this one, the plate type is more efficient, is it?
No. I'm saying the oscillator heat is more efficient. I think.
What I couldn't visualize is how is the heat exchange done between your copper pipe and your PVC pipe.
Correct. Yeah.
It's definitely not laminar flow. You say there are some.
There isn't a laminar flow. Yeah. Because
so what is the thing? How you cause the turbulence when you there? You could probably flow on a zigzag pattern or something.
Yeah. So basically, it will move back and forth.
So if there is a
modeling.
So it
there is
actually
a
doing
flow.
some
some kind of movement. So then the boundary layer is disrupted.
You
So
want to see how you look, how you observe the boundary
You
layers.
can do a CFD lah.
Yeah.
CFP.
Okay.
So basically, you have two isolated systems, right? One is the hot water going, then through this pipe, then the hot water will come back
Correct.
to the heater. Whereby you have another one is actually cold water coming and heat up, right? So it's actually two separate, but basically they're using this water pipe as a kind of heat conduction
Yes, correct.
and heat convection.
Yeah.
Can we go and look at the picture where you actually man up the PVC pipe? You show there was one with the crack on the PVC pipe. Is it after you try for 97 degrees and the PVC
No, for
pipe?
this one it's actually because there was too much stress.
Okay.
It's not because of the heat, because I haven't pumped the heat, then it broke.
It broke.
Yeah.
The sealant.
The sealant wasn't strong enough, so I
imagine
decided
that
to.
you haven't have the heat yet and it broke already. If the heat goes in, I don't know what's going to happen. Then hot water spray everywhere, very dangerous. You know. So those rings are they supposed to reinforce the?
Yeah, correct. This to reinforce the part. So instead of just depending on the sealant and the glue, I decided to put that extra layer to give the additional
Over the
strength.
top. Ring. How you fit the rings over?
Sorry.
How you fit the rings on top?
Fit the rings on top because it is.
Force fit.
No, as in it's just nice actually because
Buy
before
off the shelf, right?
Yeah,
Buy off the shelf.
buy for the shelf,
For
correct.
force fit.
Yeah.
And
Yeah, because it was a long pipe, then I machine, then you can put it as the because this one was actually a recycled part.
yes.
Because when I got the P joint, it was actually very long. So when I got the additional part, I use it as that reinforcement.
You slip it as a ring.
Mm,
over.
slip it as a ring.
Slip on is it or just?
Not really, because it's between two. Because I already cut. Then
Two pieces are like that.
yeah, two pieces.
Ah.
Then it's a joint.
Right.
So I'm interested how you do all the measurements. What kind of equipment you use to monitor the temperature?
Oh, for the temperature, I use the digital thermometer. Yeah. Then after that, for all the measurements, is usually vernier calipers and all this kind of stuff.
Did you use any data logging?
So we wanted to go into that lab view data logging, but the problem is we had to settle the issues of the leakages on. Then we had to settle the brazing issues at the same time, so I wasn't able to come up with the lab view program. So sorry, but I tried lah. It's just that it didn't came up. Yeah.
Radin, one quick question. How scalable is this system?
How scalable? As in, how can I transfer to?
Commercial.
For commercial use, actually, I can design. We can change it to maybe different. Maybe, for example, in this case, we are using a 15 mm pipe. Then the hole will be 50 mm. So we can change it maybe to a smaller hole or maybe different fittings because there's the reducers and all this kind of stuff in for PVC pipes. So in a sense, it can be transferred to a lot of different usages. Maybe even if it's design cases, we can even change it using an elbow and whatnot. So there is a lot of opportunity to change the design and scalability of it. Yeah.
Actually, his question is, if you increase this diameter, the
Oh.
diameter,
Right.
As in, if you increase the diameter. Oh, sorry. So because if I use the same study, the OFM study, I can actually scale it even bigger. Maybe go up to 75 mm. Maybe then I'll just increase it. Maybe the baffle size will be even bigger. Yeah. So
cost pressure drop.
for this case, it will be even more pressure drop, but it will still perform better than the plate type.
The plate type.
Because plate type is definitely dependent on the pressure drop.
Because pressure drop will cause problem for your compressor.
Correct. Yeah. But my oscillator 1.0 is very low as compared. So even if you increase the size, it will definitely be performing better than the plate type.
What is going to happen, alright, if you were to scale it? How much can you scale it by?
As of now, it's dependent on like what type of copper pipe that we have that is in the industry usage right now. So in some sense, if it gets bigger and bigger, or if it gets smaller, in a sense, I think the max would be to make it more effective is the baffle sizing. So to disrupt the flow of the flow of water inside. Yeah.
The baffle is this
This
ring.
Yeah, correct. So because if you scale
So
up,
you have inside there, are there two sizes of baffle or one size of baffle?
one size.
One size.
One size, yeah.
I thought there would be two sizes so that you can force the flow to go up and down. One to be attached
there's
to
also
the pipe
actually-
and another one attached to the inner pipe.
Correct. So that was actually another study that says that maybe we can do a different design, maybe two different baffles inside of the system, so make it more flow differently, or increase the heat transfer. But we haven't tried it out to test it whether it works or not.
If you were to have a baffle to attach to the copper pipe, you can have a copper baffle because it can be braced on.
Yeah, correct.
Where else, very hard to
Yeah.
attach something to the plastic pipe. I don't know how
Yes.
you're going to weld it there or that one. They use the plastic pipe. Can weld PVC or not?
Currently there's a plastic weld, but that will be for plastic purposes. But to put the copper pipe, it might be.
Inside the pipe, I don't know
Correct.
how far you can reach there because of the diameter of the pipe.
Radin, one quick last question.
Yeah.
Me,
Yeah.
Are you all trained in do CFD?
No.
No.
Yeah.
You cannot do CFD.
As of now, no. Not
Already,
yet.
You kind of
Yeah.
CFD to do this, to see
Yes,
the level flow.
not at
Not their level.
module level,
Oh.
but we from time to time we do CFD for some projects.
Oh.
Yeah.
Would be
But
interesting.
the governance that.
Yeah,
Okay, another thing, wanted to check. You mentioned that you get the reference, you get this size according to the University of Cambridge.
Yeah, correct.
So in the research paper, did they mention by doing this design how good it is, and compare with your actual one, which is in the experiment, the efficiency?
They never state. They just because that study was basically to learn about the oscillatory flow mixing instead of the heat transfer part. So I'm using that method of oscillatory flow mixing to actually test out whether it is actually heat transfer efficient or not. Because they mentioned it during the one of the part where I read it.
Okay. So basically, the design is it's kind of you randomly or benchmark based on whatever.
Yeah,
variable.
based on
Then you start to doing the experiment, right?
okay.
Okay, Radin, maybe I ask one last question.
Sure, can, sir.
Sorry. Maybe just give me an example. What's the biggest challenge you have in this project?
I think for me personally, it's more of like because it's a one-man project. So it's the lack of bounce. Like I won't be able to bounce back ideas on my own. But apart from that, I think the support from Dr. Yip and also my TSO, we were able to like do counter that. But at the same time, is the fact that maybe for me it's more of like I need that partner to do a lot of things with. Yeah, that's all. Let me say.